Personally, I always found physics to be harder, but hey, to each their own, I guess. So yeah, like I said, no recitation today, as well as I haven't finished up the test. I'm pretty sure I'll finish them tomorrow. Worst case scenario Friday, but I'm pretty sure I'll be done with them by tomorrow. I posted the solutions to the test online already, so you can look there. But you don't want to torture yourself with whether or not you, damn, I don't think I did that. You can just wait until tomorrow, we'll see where we are. We are just going to pick up with the series. Last time we spoke about two particular kinds of series. We spoke about the telescoping series. This was just one when you flesh it out. Most of the terms in your series actually cancel each other out, and then you can find the series by taking the limit. The other was the geometric series.
No, I can't.
So I left you some examples to do there, but I said I would kind of talk about that a little bit more. So this series has the form. It's a very specific form. N goes from 0 to infinity of a r to the n. Or you can start at 1, which sometimes people do. It's a r to the n minus 1. So this guy basically, when you start to actually write out what it is, the first term is going to be a plus then a times r plus a times r squared plus a times r cubed plus da da da, etc. And I told you that, let's talk about when does this converge? So here's the idea. So remember, recall, this guy converges if Sn, its sequence of partial sums. Converge. So that's what we're going to do here. We're going to look at the sequence of partial sums to this guy. So notice here that if I were to take the nth partial sum for the geometric series, that would just be like me adding up the first like n terms. So a up to r to the n. And here's one trick that's going to allow us to actually figure out what this guy is. I'm actually going to take r times this guy. Right, so this is just a finite sum. I'm just taking n terms, the sum of the first, well that's technically n plus 1 terms, but whatever. If I multiply everyone by r, notice that a times r is just ar. R times this is going to be ar squared, etc. I'm going to go all the way up to ar to the n plus 1. Now notice just by multiplying by r, I kind of get everyone in this list, except there is no a and there's an extra term here. But what we're going to do is we're actually going to subtract. So if this was equation 1, that was equation 2. If I take s sub n minus r times s sub n, then it's going to be a minus 0, this minus that, da da da. It's going to be this guy minus the guy over here, and we would be left with over here minus ar to the n plus 1. So notice that I could actually solve for a formula for this guy. This is a minus ar to the n plus 1 over 1 minus r. And so that basically means that my s sub n is going to look like a times 1 minus r to the n plus 1 over 1 minus r. And so what would this series actually converge to? Well, it converges to the limit of partial sums. So this would mean find the limit of that. Now you're going to notice certain things. This will actually depend on what your R value is. So remember your A and your R's are constants. First of all, notice that we have cases here. First of all, R equals 1, limit does not exist. Right? It'll actually divide by 0. It'll actually diverge is probably the better way to put that. It'll actually go off to infinity. You'll be able to factor the top, you'll be able to cancel out the 1 minus R, but once you allow that to go to infinity, you're still going to have R to some infinite power. Another one that should be clear is when your R is greater than 1. Now when your R is greater than 1, what's going to happen is you have a base who's larger than 1 and you're raising that to the infinite power. That's going to diverge as well. And probably it's nicer to say that, put these in absolute values, because it can actually work out for positive numbers. The last case is if your R is less than 1 in absolute value. So you can imagine like taking a half to the n when your n is going off to infinity, or even a minus a half to the n, right? If you take something that's smaller than 1 in magnitude and you keep multiplying it by itself, what actually happens? It actually it approaches 0 in either one of these cases. So in this case, your limit as n approaches infinity of a times 1 minus r to the n plus 1 over 1 minus r, this part here is going to approach 0, and so we're going to end up with just a times 1 over 1 minus r as the answer. And so we can say that this series a r to the n is going to be a over 1 minus r if and only if r is less than 1 in absolute values. So that's something that we know now. So here, this was your a and r are constants, non-zero, and your series will actually approach this value as long as your r is less than 1 in absolute values. And that's pretty much it. So I gave you this formula last time, and this is kind of where the formula comes from. So it's kind of this trick that you used. It's pretty much the same trick you used back in Calc 1 to prove that the sum of the first n positive integers was n times n plus 1 over 2. Right? So when you proved that formula, you actually did the same trick. You said 1 plus all the way up to n, then you doubled it, then you added them together, and then you did some algebra trick. Yeah. So that's actually how we got this formula. Let's actually apply it to some examples. So I believe I left you with 3 examples from last time. So basically you want to determine the convergence here. So either tell me it diverges, or tell me what it converges to. So n equals 1 to infinity of e over pi to the n plus 1. The second guy was n goes from 0 to infinity, 1 plus e over n to 4 plus 1. Last one. Ideas for the first one?
Take E over pi up.
Want to factor out an e over pi?
Yeah.
What would you be left with?
1 over pi into
What can you do with that? Yeah?
So then that's the geometric series, so R is 1 over pi.
Right, so this you can write as e over pi times 1 over pi all to the n. So now you realize this is geometric. With a equals,
E over pi and R equals 1.
no, not exactly. So you have to remember there are two variations, right? Now your a is meant to be the first term. Right? That's how you want to think of it. So it's not just going to be e over pi actually. One way you want to do this is to notice, you have to actually notice where you're starting from. You're starting from 1, which means if your starting point is 1, you need this power to be n minus 1. You need the power of the r part to start out being 0. And so what you could do is you could factor out an extra pi.
yeah, E over pi squared.
Right, it says e over pi squared, then this would be 1 over pi to the n minus 1. And so now you think of that as the geometric guy, because you need the value to work out. So this is geometric. With a is e over pi squared, and your r is 1 over pi, and you can note here that your r in absolute values is actually less than 1. 1 over pi is less than 1. So this means the series converges, and we know what it converges to. It converges to a over 1 minus r. So it's going to converge to e over pi squared over 1 minus 1 over pi. In other words, multiply this by pi squared over pi squared. So that's what it converges to. Another thing I wanted to remind you from last time is the convergence is absolute. Meaning, even if I were to throw absolute values around this thing, it's going to work. Once a geometric series converges, it actually converges absolutely. Because it doesn't actually matter whether you put the positives or the negatives there. Being smaller than 1 in magnitude is good enough to let this part go to 0 really, really fast. It's an exponential function. So, yeah, the first one actually converges. Specifically, converges to that number. The trick is just to make sure you write it in one of the two convenient forms, and that gets you to the answer. Any questions on this? Okay, ideas for this one?
Take the limit of n to infinity.
You mean of this thing?
Yeah. And that would end up, wouldn't that give you an wouldn't that diverge, cause it would be 4 to the infinity, 4 to the power of infinity.
Yeah, but on top you have e to the power of infinity. Right, you have e to the n over here.
Oh,
That actually would go towards infinity over infinity.
okay.
How would you know what that actually approaches? One way you could do it is L'Hopital's rule.
Oh, it's locked.
Another,
Can
there are other ways that you could see it. I
we
mean-
factor out a corner?
You can factor out a 4. Right, so this is really 4 times 4 to the n. And if you remember that the biggest guys control things as you go off to infinity, so that's what the limit is going to behave like. This +1 isn't going to matter when you're going off to infinity. So basically, you are really looking at the e to the n over 4 to the n. That's kind of what this guy's going to behave like. Or this looks like e over 4 to the n. Now e is 2.7, and 4 is larger than 2.7, so this actually approaches 0. So this one is actually 0, which means no info. So you might have thought of applying the test for divergence here, but it doesn't give you any information. So that limit is actually 0. So, other ideas?
Factor 1/2.
Fact what?
1/2.
Factor 1/2 from where?
Because the first term is 1/2.
The first term isn't 1/2. Where are you looking at exactly?
When n equals 0.
Okay.
There's
Wait, are you thinking of that as a geometric?
Yeah.
It's not the form for a geometric.
Can we get it in the form of a geometry?
That's what I'm asking you guys.
Can we factor out?
It's currently not geometric.
Yeah, can we factor out a quarter, but then also split the,
Okay, so we can take out a quarter.
yeah,
We'd have 1 plus e to the n over 4 to the n.
can we rewrite, would it help to rewrite it as 1 over 4 to the n plus e to the n over 4 to the n? Because then you have e over 4 to the n, and then it looks like a times pi to the n. Oh no, but it's a plus pi to the n.
But how does a series deal with a sum?
It's just you can like make them separate.
Right, series distribute across sums. That was one of the properties, right? Series don't have a lot of nice properties, but that's one of them that's kind of nice. Series actually distribute across sums, so you can actually do this. Other ideas? What can we say now?
First one is converge. A equals quarter.
Is, oh, you mean with this here? Then it's equal to a quarter, yes. But again, you're going to want to write it to look exactly like the definition. So you need it to look like a times r to the n. Notice here what I would think of it as is 1 times a quarter to the n. Right? So that's how you want to think about it. So this is a geometric series where your a is 1 for this part, and your r is a quarter. For this part, plus, I would write this guy,
1 times e over 4 to the n.
1 times e over 4 to the n. So here my a is 1, my r is e over 4. Now, of course, here your r in absolute value is less than 1. Here it's also true that your r in absolute value is less than 1. So both of these series converge individually to numbers, so the sum is going to converge. So this is actually going to be a quarter times a over 1 minus r. plus a quarter times a over 1 minus r.
So if the right side diverges, the whole sum diverges, correct?
Right, because the right side is actually equal to the left side, right? Like, this is me just simplifying, right? I mean, factoring out a 4, expanding, this is all actually equal to that. Each of these converge, so it means that the right side converges, it automatically will mean that the left side converges. This will be 1 over 4 minus 1 plus 1 over 4 minus e, or 1 over 3 plus 1 over 4 minus e would be the answer. So again, converges. How would you deal with this last example here? So, didn't give you a formula, I just wrote out a bunch of terms. Then the ellipses indicate that the pattern repeats.
So,
Say it.
There's a, you could see that it's being multiplied by negative 3 over 2.
Right.
So you could like make the form of a geometric sequence.
Right. Notice that the first term is 1 times minus 3 over 2 to the 0. Then it's 1 times minus 3 over 2 to the 1. Then it's 1 times minus 3 over 2 to the 2. Then it's 1 times minus 3 over 2 cubed. So this actually looks like a series of 1 times minus 3 over 2 to the n, when n starts from 0, goes off to infinity. So this is actually geometric. Our a is 1, our r is minus 3 over 2. Conclusions?
yeah, so absolute value of r is greater than 1, so it's divergent.
Right. Since absolute value of r is greater than 1, the series diverges. So that's geometric, but it's a divergent geometric series. Yeah.
Wouldn't it be n minus 1? For the n?
No, I only need an n minus 1 when the series starts at 1.
Oh, I see, sorry. Okay.
So that's a geometric series. And to be fair, when I mentioned this last time, but let's actually write it down so we know for sure. When it comes to series convergence in this class, there are 2 cases where you can tell what they converge to. And that is for telescoping series. If that guy converges, you would be able to tell me exactly what it converges to. And the geometric series, if that converges, you can tell me exactly what it converges to. In general, except for very strange examples, everything else we do from now on, it's going to be able to tell us when a series converges, but it might not tell you specifically what it converges to, right? That's actually a much harder thing to do in general. But that's where we're going to go. We're going to continue. I'm going to tell you about a bunch of more kind of ways to figure out what series are doing. Even though we can't specifically talk about where they're heading, we can know that they're heading somewhere meaningful as opposed to somewhere useless. So the next one, so 0 was the telescoping series. So step 0. I put it as step 0 because I don't think your textbook has a special section dedicated to it. It just kind of mentions it as a one-off. telescoping series. That was one of them. We then talked about the test for divergence, and the name says it all. It can tell you when something is diverging, it cannot tell you if it's convergent, right? So that's if you take the limit of the thing that you're taking the series of, if that does not equal to 0, you know it diverges. Otherwise, you don't know, right? You have to do something else. And then we spoke about the geometric series. And we know that that converges to a over 1 minus r, as long as your r is less than 1 in absolute value. So the third thing I wanted to talk about, I believe, is the integral test. So there is a series test called the integral test. And this actually uses improper integrals to talk about series, and we're all experts on improper integrals now, so that's good. So consider the series an. Right? N can start from 1 or 0 or whatever. Suppose we can write an equals sum of n. So this is a formula, which is a function. So I can think of an as a function of n, and on top of it, the following are applied. Your f is always non-negative, meaning your function is always outputting values greater than or equal to 0. Second of all, your f is continuous. So it's not outputting any, there are no asymptotes on, if you think of this as a function on the real line, there are no asymptotes or holes or gaps or anything like that. If I think of an as a function, it'll be a continuous function. And 2, f and 3, f is decreasing, which means it's getting smaller over time. One way you can actually check this is that your f prime is actually going to be less than 0. Right? So if you have a positive continuous function that is decreasing, then we may compute this integral. Which is going to be an improper integral because it has an upper bound of infinity, right? So this is going to be a continuous decreasing positive function, non-negative, right? And so here's the important part. The series an and the integral they'll both do the same thing. They'll either both converge together or both diverge. Right? So you can talk about this series based on what that integral is doing, and the idea is actually computing an integral will be easier than actually computing the series itself. So that's the end of the test. That test is called the integral test. Use an integral to talk about the series. This test is particularly useful. So like I said, this is going to be similar to integration in the sense that I'm going to give you a bunch of techniques that you can try on a series, and you just need to know when to choose which. So if you're looking at a geometric series, use a geometric series test. If you're looking at something else, you might say, maybe the integral test or something like that. This is particularly useful if your an is an easily integrable function. So you see something that's nice to integrate, try the integral test is what you're going to want to do. and the above are satisfied. Meaning if I think of it as a function, these three conditions are fulfilled. So if you have all of that, and at the same time, hey, I could integrate that pretty easily. The integral test is going to be nice. And the idea here is that it's a lot harder to get the integral to work than it is to get the series to work. That's why this test actually works out so nice. So remember, your series only works on the integer values. But if I pretend it's a function, it's just going to work for everything. So your series is going to be adding up some value here, right? It's going to give you some number, f of 1. And then here, it's going to give you some number, f of 2. So essentially the visualization that you can give yourself here is that you have these very thin rectangles whose area always adds up to 1. So it'll take the width that causes the area to add up to 1, and the height is going to be given by the outputs of your series. But if you turn that into a continuous function, just pretty much connect all the dots, what's going to happen is if you want to compute, say, the integral from 1 to infinity of f of x dx, that is actually going to find the area under everything. So not only is it measuring the area of these rectangles, it's measuring the area of all the in-between parts too. So the thing is, if that guy gives you a constant, then for sure, if I erased all these fillings, that would still be a constant. It will still be a finite number. It's much harder to get the integral to work out than the actual series to work out. Because the series has gaps in it, whereas the integral doesn't. So let's do some examples of that one. So an integral test is another option. For example, I don't know how many. I mean, at the end I'm going to tell you a summary and I'll probably give you some general examples. But in the meantime, I think I only put one example here. Look at the series, n goes from 1 to infinity of e to the 1 over n over n squared. So you see something like that. Now, one thing you can notice is that what you can do is consider the function f of x equals e to the 1 over x squared. One thing you'll notice is that f of x is always going to be non-negative on that interval, on 1 to infinity, right? Your exponential is never going to output a negative number, and x squared is never going to output a negative number. So you're always going to have a positive number divided by a positive number. So that's true. 2, another thing, f is continuous on this interval. You can know that because you're never going to be divided by 0 because your x is never going to be 0. So the 1 over x is always going to be defined, and e to anything defined is always going to be defined. So the top is always defined. The bottom is an x squared, and your x is 1 or bigger, so that's never going to be 0. You're never going to divide by 0. So that's always going to be defined, and the whole thing is going to work out nicely. You have basically some rational expression where none of the denominators are going to 0, and otherwise we have exponentials and polynomials. That's going to be continuous. This will work out. And lastly, f is decreasing. Now, there are a couple ways you can show this. One, it's kind of common sense. You have a denominator getting larger, because if you look at e to the 1 over x squared, notice that the denominator is getting bigger as x gets bigger. Gets larger as x approaches infinity. You can also notice that this guy gets smaller, because you're taking a larger root. So it'll be the square root of e at some point, then the 4th root of e, then the 5th root of e, then the 100th root of e. The more roots you're taking, the smaller the value is going to get. So we're getting a bigger denominator and a smaller numerator. Overall, the thing is going to get smaller. Another way to see that is to actually just find the derivative. Or you can find f prime. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. What you're going to notice is that this is going to be minus 2x plus 1 times e to the 1 over x to the 1/4. Now this part is always positive, x to the 4th is always positive, and we have a negative sign on the outside. So this is always negative. So a couple ways to check that that is decreasing. So here I have something non-negative, it's continuous, and it's decreasing, and you know what? That's actually not hard to integrate. So now, if you consider the following integral, 1 to infinity, because I want it to match up to like the series. How would I integrate that?
U equals 1 over x.
Right, u equals 1 over x, your du is going to be minus 1 over x squared dx. So minus du is going to be 1 over x squared dx. And of course, this part, u equals 1 over x means if x equals 1, your u is going to equal 1, and if x equals infinity, quote unquote, your u is going to be 0. So this integral, let's call it I, is equal to 1 up to 0 of minus du e to the u. Or in other words, that's going to be 0 to 1 e to the u du, which is just e to the u between 0 and 1. So that's e minus 1. So that guy converges. So this is a convergent improper integral. Therefore, by the integral test, in fact, I don't know what it converges to, let me make that clear. But I know for a fact it's going to be less than whatever that number is, right? Because the integral is always going to be bigger, because it's filling in gaps that the series doesn't have to worry about. So whatever that converges to, it's going to be smaller than e minus 1. I just don't know exactly what it converges to. But I know it converges. This is the integral test.
On a test, like, how much work would you want us to show? Would you want us to prove that it's greater than or equal to 0, it's continuous, and it's decreasing, and then...
On a test, I would in most cases, I would expect you to write everything I wrote except probably this part.
Yeah.
I do expect you to mention that it's decreasing, even though you might not prove it, but just so that I know that you thought of it. You know, it wasn't something that you forgot to
So we don't have to
worry
prove
about.
that it's decreasing.
But you won't have to prove it's decreasing.
Right.
I'll let that slide. But it has to be decreasing for you to do this. So conversely, if you're doing a situation where it's actually increasing, but you just write out it's decreasing just so you can use this test, like I'm gonna know that you don't know what you're talking about because it's not decreasing, right? But yeah, if it's decreasing, I'm gonna expect you to know how to check that because you know Calc 1 already if you're here, so you'll know how to check that it's decreasing. So I'll trust you, but other than that, yes, once you write this down, I expect you to tell me, oh, if I think of this as a function, it's positive, continuous, and decreasing, and the integral actually converges, so this converge. So that's basically how I would want to say. So whenever you're going to use some test, so ultimately you're going to make some conclusion based on a test. So whenever you want to say, oh, I'm using the integral test, or I'm thinking of this as a geometric thing, or blah, 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 you need to show me that the conditions for the test you're using have been fulfilled. And you have to at least mention it. So that's the integral test. Yeah, that's it for now. Last thing for today, there's something called a P-series. So like we have a geometric series, this is called a P-series. So these are series of the form one over n to the p, where p is a constant. Okay, so it's called a P-series. So notice that if we set f of x equals 1 over x to the p, and our p is larger than 1, then f is going to be positive, it is going to be decreasing, and it is going to be continuous on 1 to the infinity. So in fact the integral test does apply here. Now we know from the last section that if I were to take the integral from 1 to the infinity of 1 over x to the p dx, it converges if and only if our p is larger than 1. So this means, by the integral test, I can prove another test. The series 1 over n to the p converges if and only if p is larger than 1. And this is called the P-series test. So pretty much you see anything that looks like 1 over n to the p, you will be able to use this test to talk about its convergence by this theorem that we proved for improper integrals. So, examples. Determine the convergence of the following. So yes, I already told you the answer to this. Just a reminder. The harmonic series is actually a P-series. 1 over n squared. I also told you guys about that. Here's another one though, 1 over the radical of n. So just do those. So you're going to say, write it in the right form, and then basically say, oh, I'm thinking of this as a P-series, and it's going to converge or diverge based on some condition. So write that out. We'll pick up those tomorrow and move on to some other tests. So ultimately we're going to cover about 10 of them, and I'm going to tell you when you might choose one over the other. So we'll pick up with that tomorrow.